Here's what you should know about support vector machines for VCE algorithmics. A support vector machine aims to separate two sets of data using a range of attributes so that the same attributes can be used to predict which class some other unclassified data belongs to. For example, a spam filter might look at 1,000 emails which have already been labeled spam and not spam. These are the training data. We count the number of words in each email and the number of times the word free is mentioned, and we plot these on a graph. We aim to draw a line which separates the data with the largest possible margin. The support vectors are the points which are closest to the boundary. Now, when an unknown email appears with a particular number of words and the number of words of free, we can make a good prediction as to whether or not it is spam. Sometimes a straight line can't be drawn. The data is not linearly separable. For example, this chart shows the risk of a particular disease with age. We can see that the risk is low for very old and very young people, but we can't draw a single straight line to separate them. So we use a kernel trick to transform the data, adding another dimension. In this case, we apply a quadratic transformation, and now we see that a line can be drawn. We can extend into as many higher dimensions as we like. The line between the two datasets is called a hyperplane. However, using too many dimensions reduces the data density and makes it easier to run into overfitting. We'll talk about this when we consider problems that can occur during modelling. Consider the following data. It's clear where we would draw a line and there's a nice wide margin. But suppose we have a couple of points which don't fit the general pattern. If we insist that our margin is 100% accurate, we end up with a boundary that doesn't really represent our data. Or we change the hardness parameter and allow some data to be misclassified. Then we get a better general fit, which will perform better on unseen data. However, if we make it too soft, we could end up with a boundary which doesn't really capture the patterns in the data at all. Still, an underfit boundary might be better on unseen data than an overfit boundary. It's hard to really compare. It's like asking people, do you like being too hot or too cold? So, overfitting can happen if we try to make our model too precise with limited data, either with a very hard margin or lots of parameters that fit the noise of the training data, raising it into too many dimensions. It performs well on the training data, but poorly on unseen data. Underfitting is where we are not precise enough, perhaps because of an overly soft margin. It will probably perform poorly on all data. To avoid either problem, we can use cross-validation. In its simplest version, we keep back some of our training data and use it to test the model we develop with the rest of our data. The cost of this is that we have to make a model based on less training data to start with. Leave a comment if you have any questions or if you'd like another topic covered.